Hi everyone. For those who are students of Miss Jessel, my name is Miss Trinchere and I am the other AP Psychology teacher at Northwood High School. So today I'm going to talk to you all a little bit about statistics in psychology. So basically, just to frame it all, the past several classes we've been talking about different research methods in psychology. How do we conduct research like correlational studies, descriptive research, and experiments? But now we're going to take a look at, once we have some data, how do we actually interpret that data? And that is where statistics comes in. So yes, there's a little bit of math involved here, but it's with a larger understanding of being able to interpret data and results from studies. So just keep that in mind as we go through this information here. So the first thing to understand is why we need statistics. And the main reason for that is because it can be really easy to misinterpret findings in studies, because we can portray data in different ways that can make it look like something that it actually isn't. So what are we talking about here? I'm going to skip ahead a couple slides. If I skip any slides, feel free to go back and look at the slides on your own later. So for example, one thing you might see is a study showed women taking a certain birth control pill had a 100% increase of developing blood clots. However, what really might have been the case is that if people who did not take that pill, they might have had a 1 in 7,000 chance of developing a blood clot. Those who do take the pill might have a 2 in 7,000 chance of developing a blood clot. So that does mean, yes, there is a 100% increase from 1 to 2 of people potentially having a blood clot if they take this certain birth control pill. However, that is only one actual additional number. So it's really important to understand statistics and the fact that you really have to make sure you're looking out for the way people word things, because you can very easily get misled by the way people frame things. So in psychology, there are two main types of statistics that we use. The first is called descriptive statistics, and the second is inferential statistics. So exactly like it sounds, descriptive statistics, you are just trying to describe using your data. So that means that you're trying to describe a population or a set of data that you have. And the main thing that we use with descriptive statistics are our measures of central tendency. And we'll talk in a couple minutes exactly what that means, but measures of central tendency meaning mean, median, and mode. And also in descriptive statistics, we use measures of variation. And our two big measures of variation are range and standard deviation. Whereas with inferential statistics, you are really trying to determine the relationship between variables in your sample. And the main point here is you want to be able to infer or predict trends on an entire population based on data that you have in a sample. So descriptive, you're just primarily trying to describe what does our data look like. Inferential, you're trying to decide how can we use this data in a meaningful way. How can we take what we learned about a sample and then apply it to a general population? And here's also another image you can look at to understand a little bit more the difference between descriptive and inferential. Descriptive, you're just describing the group you were looking at. Inferential, you're looking at your group that you were studying, but then figuring out how can I generalize it to everyone else pretty much. And yet another way to put it simply if you want to check that out as well. So diving a little deeper into descriptive statistics, like I said, it's using numerical data to measure and describe characteristics of groups. And by the way, as I'm talking through this stuff, definitely feel free to add some definitions or examples into your slide decks as we go through this information. So with descriptive statistics, we definitely want to use our measures of central tendency. And so if you think about what that sounds like, central tendency, that means you're trying to measure where the data all goes together, and that is towards the center. So the data tends to gather around the center. So we use 3 different ways to measure that: the mean, the median, and the mode. And then we also want to measure variation. So how varied is our data? If it's not all clumped together right in the middle, how far does it go below and how far does it go above? So those 2 ways that we measure variation are through range and standard deviation. So before we look at exactly what those things mean, I just want to mention first that statistics can be displayed in two primarily different ways that we're going to focus on, one being a bar graph and the other being a histogram. They are super similar, but there are some differences that you want to make sure you understand. It is possible in the AP test that you will have to create your own graph and be able to accurately label the axes and your information on the graph, or you have to be able to identify information on a graph. I wouldn't ever expect it to be super complicated information that you'd need to graph, but you should generally understand the basics about how to graph some statistical data. So bar graphs and histograms are very similar, but there are a couple of differences. A bar graph, you are primarily, just as this is saying here, you're primarily looking at categories of information. So things that aren't really numerical, meaning in this example here, like countries. So bar graphs focus on categories that you're graphing, whereas histograms focus on number ranges. So you're actually putting numbers there between 100 and 350. You're measuring something that way. Visually, one other difference is that with a bar graph, there are gaps between each bar. With histograms, the bars are lined right up against each other. There's no gaps. All right, so that's just generally what are the differences between bar graph and histogram. Those are two ways that we can graph. And hopefully you know from some other classes that along this horizontal axis here, that's the x-axis, and the vertical axis is the y-axis. So definitely make sure whenever you have to create a graph, you always have to make sure that you label your axes what they are. So for example, down here it would be countries, and over here it would be money, something like that, depending on whatever you're trying to measure. So like I was saying, sometimes statistics can mislead us a little bit. So for example, if we look at this bar graph here, you might think just by looking at these different brands of trucks that our brand, if we're trying to sell this truck, our brand is the best truck because it functions super, super well after 10 years still. Almost all of our trucks are still functioning after 10 years. But brand Z is horrible. They have hardly any that are still functioning after 10 years. However, is that really the case? Let's look at this graph here, which is showing us the exact same data, but in a slightly different way. So now, is there really that much of a difference between our brand and brand Z? This is actually the exact same data that we're showing here. It's just shown differently. So let's look at them side by side. The main difference here is the way that we labeled it on the y-axis, meaning our intervals. So for this first example, it was just the intervals were measured by 1, so 95, 96, 97. In our second example, they measured in intervals of 10. So that makes it look like in our first example that there's these huge differences when really it's just these small little percentages of a difference. In the second one, you can actually tell there's really just slight differences between each, but it's not that big of a deal. So again, just be wary of the way that you see statistics presented and the way that you present statistics as well. You don't want to mislead people. So going back to now our measures of central tendency with mean, median, and mode. Mean is hopefully, all three of these are hopefully things you've heard before in other classes, but a mean is the average of a set of numbers. And the way that you calculate that is by adding up all of the data points that you have and then dividing them by however many points of data you have. So for example, if I have 10 different data points, I'd add them all up and divide by 10. That's my mean. The median is the middle score in a distribution. So that means if you line up all of your numbers from lowest to highest, which by the way, definitely make sure you do that. Sometimes we might give you data sets that are not arranged in numerical order. The first step is you have to arrange them in numerical order. And then you want to see if you just cross off on each end, go in one by one, what's your middle value there? If you end up with, if you have an even amount of data and there's no middle value, you have to take the average of the two that are in the middle. And finally, the mode is the most frequently occurring data point in the distribution. So what's the data point that you see over and over again? So if you want to try out this data set here, feel free to do so. Don't forget, the first thing you should probably do is make sure to arrange these numbers in numerical order. If you want to practice these yourself, go ahead and pause the video real quick and you can solve them. But otherwise, I'm going to share the answers with you so you can check your work. So as long as you made sure to arrange them in the correct order first, your mean that you should have found should have been 5.56. The median would be 5, and the mode would be 9. All right, so check yourself with those answers, see if that's what you got as well. So let's look at these things all graphically now. So for example, if we are trying to represent the income per family in thousands of dollars, that's what we're trying to do here. So we have a bunch of people who have income in this range over here, and only a couple who are a little bit higher up. So on this graph, we can see our mode, median, and mean. So let's look at them a little more closely. This points out that the mean is not always our best descriptor of data. So for this example, you can see the mean comes out to be 140, but look at where all the data is, it's all way lower than that, between 30 and 100 mostly. So in this case, the mean is not really a good representation of what the data really shows. The mean makes it look like the income is deceptively high. And what that means is that this distribution is skewed. So if it's skewed, that means that most of the scores or the data fall on one side of your scale and then just a few on the other side. So everything that I circled here, that's kind of showing how it's skewed, that there's all this data here and there's hardly any on the other side. And we do want to make sure we know the difference between a positive skew and a negative skew. And just one more point about that real quick. The reason why data can end up being skewed as well is that there might be a point called an outlier, which is a data point that's extremely different from the remainder of your data. So as I mentioned, most of the data tends to fall between 30 and 100. However, there's a couple of outliers out here, especially this guy that's 1420, which is way, way higher than the rest of our data. So that person would be an outlier here. And therefore, that skews our data. So let's look at the difference between a positive and a negative skew. A negative skew here, most of our data is falling at this peak point here. That's where your mode would be, because that's where most data tends to be. However, you have some outliers over here to the left side. That means it is skewed negatively. So one quick, easy way you can tell which direction the data is skewed is by which way the tail of the graph is going. So in this case, if you look at your arch here, the tail is primarily going off to the left. So that means it is skewed left or negatively skewed. If something's skewed to the left, it's negative. If something's skewed to the right, it's positive, just like on a number line. Obviously over here, you can see with a positive skew, there's your outliers would be more towards your right side. So it is positively skewed because that's where the tail end of your data is. So basically that would mean that the mean is more positive or greater than the rest of your scores. Most of the scores fall right here, but that little tail end is going to pull your mean up higher there. So the mean ends up being higher than all the rest of the data. That's why it's called a positive skew. So definitely make sure you know that figuring out the skew is not based on where the bulk of the data is. So you might accidentally think that because all the data is at this peak point here, that means it would be more negatively skewed. It's not. It's actually where the tail is, because that means that it drags the mean up in that direction. All right, so that's your simple trick, is whenever you see you're trying to figure out the skew of data, if the tail goes to the left, it's negatively skewed. If the tail goes to the right, it's positively skewed. If the data pretty much looks symmetrical, that means it is a normal curve or a bell curve, which we're going to talk about a little bit more in a second. And definitely make sure you check out this AP exam tip here about outliers and measures of central tendency. So if you want to look over this comprehension check, feel free to do so real quick. I'm about to tell you the answer in a second, so pause if you want to read through it. Our answer here for this one would be mean. The mean is the one that can skew the data based on outliers. So now we're looking at range and standard deviation. The range is the difference between the highest and lowest score in your distribution. So basically you're trying to figure out what's the lowest point in my data and what's the highest point in my data. And that helps you figure out that all of the rest of your data must fall somewhere between that range right there. So here's another example if you want to go through and try to solve the mean, median, and range on your own, if you just want to practice a little bit more. But a quick, simple, easy practice for the range is what's the range of this following data? Go ahead and try it on your own real quick. So I'll tell you the highest number is 80, our lowest number is 12. 80 minus 12 would be 68. So that would be our correct answer there, letter A. Now moving on to standard deviation, another form of measuring variation. This one can get a little complicated, so stick with me here. Standard deviation is trying to measure how much the scores vary from the mean. So you know most of your data is where the mean is. Your standard deviation is trying to find out how far away from the mean does the rest of our data fall. And there's a little tip about how to calculate standard deviation here. It's highly unlikely that you would ever have to calculate standard deviation on the AP exam because you do not get a calculator on the AP exam. So any numbers that they give you of mathematical things you'd have to do should be pretty simple. So it's very unlikely that you'd have to calculate standard deviation, but if you want to check out how to do it, feel free to look at this part here. But it is important to note this part at the bottom here, that the standard deviation shows whether scores are packed together or if they're dispersed. So the more that all of the data is packed together, that means you will have a smaller standard deviation. And that's probably a good thing. That means all of your data is going to fall within a similar point. So the more packed together your data is, that means the more similar your scores and the smaller the standard deviation because they're not varying much. If your standard deviation is really high, that means your scores are very dispersed or varied. They're kind of spread out all over the place. So let's try this quick example here. Which of the following standard deviations depict a data set that is more similar than different, meaning most of our data falls together? Go ahead and guess for yourself real quick. Our correct answer here would be 1.5 because that is our smallest standard deviation, meaning all of the data falls close together. There's not a lot of variance there. So something else with standard deviation that's really important to understand is this concept of the bell curve, and that was what I kind of alluded to a couple minutes ago. So the bell curve, it's also called a normal curve, a normal distribution. They all mean the same thing. That's just basically describing what most of the time, what our data tends to look like. So the reason why it's called a bell curve is because it has this bell shape and it is symmetrical, meaning it's roughly the same on the left side and on the right side. And a bell curve or a normal curve means that most of the scores fall near the mean. So if it's a normal curve, your mean actually falls right in the middle where that peak is. All three of your mean, median, and mode would be at that same peak point if it's a normal curve. Don't forget, if it's skewed, the mean would be dragged one way or the other. But with a normal curve, mean, median, mode are all right in the middle. And a normal curve is saying that most of your data tends to fall right there at that middle point. That's why there's this big bell shape in the middle. And that there are fewer and fewer scores near the extremes. So most of your data is in the middle. With this whole thing that's going on here, if you're trying to figure out the standard deviation, meaning how far away from the mean is our data, we have to kind of understand this graph here. So it is saying that if we, for example, take intelligence scores, and the Wechsler Intelligence Scale is this one thing we can use to measure intelligence that we'll mention later on in the year. But basically, it's important to know that the average IQ score with this Wechsler Intelligence Scale is 100. So whatever number is in the middle of where that peak is, that would be your mean when you're trying to find standard deviation here. So the mean would be 100. In this case, the standard deviation would be 15. Because if you look, this first point here is one standard deviation above the mean. Our next point, 130, is 2 standard deviations above the mean. And this last point here, 145, is 3 standard deviations above the mean. On the other end, again, if we start with 100, 85 is 1 standard deviation below, 70 is 2 standard deviations below, and 55 is 3 standard deviations below the mean. So if you're trying to figure out what actually is the standard deviation, If you go from the mean up to one standard deviation, 100 to 115, that's a difference of 15, and therefore one standard deviation equals 15. You can see it the other way as well. If you go from 100 and then one standard deviation below the mean, 100 to 85 is also 15. If we take a look at these numbers here, you can see there's a bunch of numbers all over the place. Those percentages are very important for you to know. So you want to make sure that you memorize those percentages. And there's this little rule you can remember. It's not the cleanest rule, but it can help you. And it's called the 68, 95, 99.7 rule. And what that means is that if you memorize each of those numbers, 68% of our data in a normal curve will fall between one standard deviation below and one standard deviation above the mean. So that's what this arrow is showing us here, that 68% of our data, which means most of our data, is falling between one standard deviation below the mean and one standard deviation above the mean. The 95 comes in because that means 95% of our data falls between two standard deviations below the mean and two standard deviations above the mean. So that is that point from 70 to 130. That's 95% of our data. And lastly, the 99.7 is saying from 3 standard deviations below and above the mean, 99.7% of your data falls there. Those are all rough estimates. They're kind of a little bit more precise than that. But generally, if you remember 68, 95, 99.7, you would be fine. You could also memorize it by just looking at half of the graph here. So if you look, if you're only looking standard deviations above the mean, then you could memorize that, well, actually you could do it this way. Yeah, sorry. So if you look between the mean and one standard deviation above, that's 34% of your data because that's 68 divided by 2. If you want to then look at your next point here between between 1 and 2 standard deviations, that's 13.5% of your data. And then between 2 and 3 standard deviations, that's 2.5%. So up to you how you want to memorize it, but you should know those percentages. And we're going to practice something with those percentages in a second. Here we are. So if we look at this normal curve here, we want to figure out what is the range of possible IQ scores for a student whose IQ falls within one standard deviation above and below the mean. So that means we want to make sure we are looking at one standard deviation below the mean and one standard deviation above the mean, and we want to find out what are the possible IQ scores that this person might fall between. So again, if 100 is our mean, that's the middle. One standard deviation below is 85, and one standard deviation above the mean is 115. So that means this person's score would fall somewhere between 85 to 115. All right, that's all that this one is saying. Another little example here that you might want to try on your own to actually put it into other terms is that some kind of soda machine dispenses small sodas with a mean weight of 4.9 ounces and a standard deviation of 0.1 ounces. So we want to know what is the interval, again like that range, what is the interval that accounts for 95% of all the small sodas it dispenses? So if we look here at our standard deviations, we know that 95% of our data means it's between 2 standard deviations below the mean and 2 standard deviations above the mean. That's where 95% of our data is. So what we would want to do in order to graph this out, and I can show you real quick on a bell curve here, our mean data we know is 4.9, so that would be our middle number that we have here. And we know that a standard deviation is 0.1 ounces. So if I draw us a couple tick marks here and map out what 1, 2, and 3 standard deviations would be, if we know our mean is 4.9 and one standard deviation above the mean is 0.1, that means you would add 4.9 plus 0.1 equals 5. So one standard deviation above the mean is going to be 5. Similarly, then you would take 5, add another standard deviation, which is 0.1, and you know that would be 5.1. Moving backwards now from the 4.9, which was our mean, if you subtract 0.1, you know that that would be 4.8, and then subtract another 0.1, which is our second standard deviation, that would be 4.7. So if we're trying to figure out that our data that falls between 95% here, that would be, we know it's 2 standard deviations below the mean, which is this point right here, and 2 standard deviations above the mean, which is this point right here. So the data, the range of where our data falls from 95% of our data falls between the numbers 4.7 and 5.1. All right, so go ahead and take another look at that if you would like to. But that is putting into practice a little bit more what standard deviation is. So our last bit here, we just covered descriptive statistics where we're just describing different data. Now we want to move to inferential statistics where we want to see how does what we just calculated, different kinds of data we have, how can we make that meaningful and apply from our sample now to the general population. So with inferential statistics, it's numerical data, again, that allows you to generalize something from your sample to being true to your population as well. So if the sample is representative, that's when it would be good for you to be able to generalize it to the population. You also want low variability in your data, and you also want to have a lot of people in your sample as well. That way it hopefully is more representative of your population. So this is the really, really big part about inferential statistics we need to understand, and that is statistical significance. So I want to point out real quick that in general, the word significant means that something is important. That is not necessarily true in psychology. When we're talking about statistical significance, that doesn't necessarily mean that is something important or not. It's just kind of this term that we use to figure out how to interpret our data. So statistical significance is a statement of how likely it is that a result occurred by chance. And the way that we represent statistical significance in statistics is by using the lowercase letter p. So it's called our p-value. And the big key thing here is in most studies that we do, you want to have a p-value of 0.05 or less. So you want p to be less than or equal to 0.05 in most studies. That would mean that it is 95% likely, so that we got 95 if you did 100 minus 5, because 0.05 is like 5%. So if you do 100% minus 5%, you get 95%. So a p-value of 0.05 would mean it is 95% likely that the results we got in the study did not just occur by chance. So that means we can pretty much figure out that whatever our outcome was in our study is because of the thing that we manipulated. So to put this more simply, we want p to be less than or equal to 0.05. That means that whatever thing you looked at in your study is significant. So again, another way to put it is that whatever results you see in your dependent variable are extremely likely to have been caused by the independent variable that you manipulated. So that means it's probably because of your study that you saw these results rather than it just happening to randomly happen by chance. So it's a good thing. It means this thing occurred because of what you did in your study. So let's do one last quick example here to try this out. If we're looking at the effectiveness of a new weight loss drug, and we have group A who receives the drug, and after 7 weeks of taking this weight loss drug, they have a mean weight loss of 4 pounds. Group B does not take the drug. Instead, maybe they just do the regular workout routine that they try to lose weight. They have a mean weight loss of 1 pound in 7 weeks. So group A loses 4 pounds, group B loses 1 pound. Our p-value is 0.01. That's something that was calculated. You should never have to calculate p-value yourself. It's a really complex statistical thing, but p-value might be given to you. In this case, it's 0.01. So what we want to figure out is, can we conclude that the difference in weight loss that we see between group A, which was 4 pounds that they lost, and the weight loss in group B, which was 1 pound, can we conclude that that difference is due to our weight loss drug? Or was it just kind of random chance that we happened to see more weight loss in group A than group B? So in other words, are our results statistically significant? That's what we're trying to find out. And the fact that our p-value is 0.01, which is less than 0.05, so remember you want p to be less than or equal to 0.05, the fact that the p-value is 0.01 would mean that the likelihood that the difference in weight loss between the two groups is due to chance would be 1%. So there's only a 1% chance that our difference we saw was just due to chance. If you flip that and say it the other way, that means it is 99% likely that we saw the difference in weight loss between the two groups because of this weight loss drug. So that means we are almost pretty absolutely certain, we are almost positive that the difference we saw in weight loss between the two groups has to be from this drug. That means that our results that we saw are in fact statistically significant. Okay, so that's what a p-value of 0.01 means, or anything that is 0.05 or less. That is what that would mean. Your results are statistically significant, which means whatever results you saw probably were not due to chance. They were instead due to the study that you conducted. Okay, and one last quick comprehension check for you. If you have a statistical significance of 5%, which is 0.05, which of the following is an accurate interpretation of this finding? You can take a second and pause real quick and read through the responses. But I will go ahead and tell you that letter B would be our correct answer here, that 5% or 0.05, that is our minimum result that's typically considered statistically significant. You wouldn't want any number greater than that. You wouldn't want 6% or 10%, anything like that. That's getting way too high that now it's no longer statistically significant. So 5%, 0.05 is our cutoff point of what's considered statistically significant. So that is it on our portion of statistics in psychology. I hope that this video is helpful for you. If you need to go back and rewind or pause certain parts, feel free to do so. And absolutely feel free to reach out to myself or Miss Jessel if you have any questions about any of this information. Thank you all very much.